Alright, firstly I will briefly explain the concept of particle separations. In a general, particle separations refer to the process of dividing particles into a different group based on their physical properties, mainly size and also density. Why is it important? Because this process is crucial for purifying substance, analyzing complex mixture, and also improving the industrial process. Alright, there are two main types of separations. That is, firstly is a size-based separations, where the particles are separated using a filter or meshes, such as in screening or air classifications, while the second one is a density-based separations, which uses gravitational or centrifugal force, as seen in the hydrocyclones and flotations process. These methods are widely used in the industry, such as solid waste management and food processing. Overall, particle separation is a fundamental unit operations that play a vital role in the chemical engineering and the material processing.
Assalamualaikum and hi, my name is Nur Aina Bagusbente Azman. Next, I'll present about the first application of centrifuge in food and beverage industry. Centrifuge is used to ensure the purity, yield, and efficiency. In general, centrifuge process occur with the less than components move toward the direction of centrifuge axis, while the denser will move away from the axis. The centrifuge process is based on the size and density, where if the size is bigger and the density is denser, the separation will be faster. The example that I use is wine processing. In laboratory, centrifuge process is done for wine processing to separate yeast cell, bacteria, and sediment for microbiological testing to ensure quality control. Other than that, it will help industrial sector to reduce the time required to find a good formulation to make a high-quality wine because the process of wine fermentation can affect its shelf life. Lastly, if it will allow winemaker to determine optimal conditions for the sediment removal. The commonly used centrifuge is benchtop centrifuge, where the sample in a rotor is partially rotating, then it will create force that separate compound based on the density difference. Next, for the wine processing in industry, centrifuge is used to clarify liquid, remove sediment, thus improving the taste and transparency of the final product. The commonly used centrifuge is the G-stack, where the function of process is based on the fast rotating ball with a speed at approximately 6,000 rpm, in which the separation will occur. The liquid feed will enter the centrifuge through inlet and speed up to the speed of centrifuge, and then the feed is rotated radially outward in the distributor and dispersed to the G-stack. As liquid moves toward the center of the ball, it will separate from the sediment. Then, this separated liquid leaves the G-stack by move upward and exits the ball via a centripetal pump that known as a parent disc. The separated sediment, which is heavier than liquid, is driven to the ball rim and collects in the sediment space outside the G-stack. The sediment are discharged through several openings in the ball wall. Then, the sliding ball at bottom allows for the intermittent adjustment discharge. After that, a specific liquid force acting on the underside of the sliding ball causes it to be pushed upward against a seal ring.
Now, let's look at how these centrifuges are applied in laboratories. Although benchtop decanter centrifuges are smaller, they function based on the exact same principle, using centrifugal force to separate solid particles from a suspension. But in a lab setting, their purpose is focused on research, testing, and simulation. In bioprocessing, they are used to separate biomass such as microbial and yeast cells from fermentation broth. They are also used to recover protein-rich supernatants, especially during early-stage drug development or enzyme production. In environmental laboratories, researchers use benchtop centrifuge to evaluate starch under different chemical conditions. This is helpful in testing how effective a treatment chemical is before it's applied at a full scale in wastewater plants. In chemical process development, the centrifuge helps simulate industrial sedimentation process in small volumes. Researchers can vary the rotational speed, residence time, and feed conditions to test how materials behave under separation force. What makes this centrifuge especially valuable in labs in the high level of control and repeatability. They help model real-world process on a manageable experimental scale, making them ideal for optimizing process before committing to large-scale productions. Despite their compact size, they are highly efficient, user-friendly, and essential in bridging the gap between theory and industrial applications. Let's begin with the industrial applications of decanter centrifuge. These machines are highly efficient for separating mixtures, especially slurries, by density using centrifugal sedimentation. When the balls spin at high speed, much faster than gravity alone, solid particles, being denser, move outward and form a layer along the ball wall. A rotating screw then continuously pushes the solids towards a discharge point, where the lighter liquid flows out separately. This process runs continuously, making it ideal for industries that handle large volume. In wastewater treatment, decanter centrifuges are crucial for sludge dewatering. They help remove excess water from sewage sludge before final disposal or incineration. This is not only reduces waste volume but also cuts down transport and treatment costs while meeting environmental regulations. In the food and beverage industry, these centrifuges are used to extract starch from corn, clarify juice, and recover proteins from dairy whey. Because the system is enclosed, it reduces the risk of contamination and is suitable for hygienic processing. In the oil and gas sector, decanter centrifuges are used to treat drilling mud. They separate fine solids from the reusable liquid, improving drilling efficiency and reducing waste disposal costs. This also supports sustainability by allowing the fluid to be reused. The main benefits of using decanter centrifuge at industrial scale include minimal operator involvement, consistent performance, and energy efficiency. The system can also be adjusted to suit different feed materials by changing the rotational speeds and feed rate, making it highly adaptable.
Next is sedimentation. Sedimentation is the separation or concentration of suspended solid particles from a liquid by gravity settling. Suspended material may be particles originally present in the source of water. When solid particles are suspended in fluid, gravity causes them to sink. It is commonly used to separate solid particles from liquid, such as wastewater treatment or sludge separation. Next is flotation. It's the complementary process to sedimentation and is used to separate particles or droplets that are less dense than surrounding fluid. For laboratory application, commonly used in the environmental analysis of suspended solids in water sample. As we know, sedimentation relies on gravity and settling to achieve solid-liquid separation. So this application will allow particles to settle or float naturally over time in a column of liquid. So the heavier particle begin to settle to the bottom due to their high density, while the lighter or the less dense material may remain suspended or float to the surface. So the resulting flux left by the gas bubble, which can be collected from the surface of the water. As you can see, the figure above tells the general scheme of coagulation and flocculation processes using a coagulant and flocculant agents to interact with the suspended particles and other impurities. So as you can see, figures in the laboratory application, we have the coagulation, flocculation, and sedimentation. If we look at the sedimentation part, we have the heavier particle begin to settle down at the bottom due to their high density. Meanwhile, the smallest or the lighter material will begin to suspend or float to the surface. In the laboratory, we can also use the flotation technique, which is used to separate fine particles such as microorganisms, proteins, or suspended solids from a liquid solution. The process involves introducing fine air bubbles that attach to the specific particle, causing them to float to the surface for easy collection. This technique is commonly applied in biotechnology and microbiology research, particularly for recovering cells, protein, or bioactive compound from the culture media. Next, for the industrial application, sedimentation is widely used for separating solid particles from the liquid based on density differences. So the large settling tanks or clarifiers allow heavier particles such as sludge or suspended solid to settle at the bottom under the influence of gravity. This method is commonly applied in wastewater treatment plants, mining operation, and food processing industries to remove the solid waste from liquid streams efficiently. For example, like wastewater treatment plants, in which sedimentation is used in primary and secondary treatment stage, to remove the solids from sewage, and industrial influence to help reduce the load on the further filtration or biological treatment. As we know, this topic is about the sedimentation and flotation, right? So in this process, air bubbles are introduced into a mixture, and specific particles attached to the bubbles due to their hydrophobic. This bubble particle cluster then rise to the surface, forming a froth layer that can be skimmed off, effectively separating them from the rest of the mixture. This method is highly efficient for separating low density or hydrophobic materials and is used across various industries for both resource recovery and wastewater treatment. So, as I mentioned, the laboratory application and industry application, this proves that the sedimentation and flotation is a really good example for the separating particles based on their density.
Now, let's summarize the key takeaways and reflect on why these separation techniques are indispensable across industry. First and foremost, particle separation is the backbone of purification and analysis. Whether it is isolating protein for biotechnology or recovering mineral in mining, these processes ensure we can extract valuable components efficiently. Without that, industry work face higher costs, lower purity, and unsustainable waste. We have explored two core approaches, size-based and density-based separation. Let's compare them directly. Size-based method like sieving and centrifugation excel in food and pharmaceuticals. Think of separating yeast from wine. Density-based technique such as flotation or sedimentation dominate mining and wastewater treatment where particle mass is critical. Each method is tailored to the material's property. Why does this matter? Because choosing the one method could mean losing 20% of your product or worse, contaminating it. Okay, let's talk about the number. Certification isn't just fast, it is transformative. For example, Dissenter centrifuge reduce sludge volume by 50%, slashing disposal costs. In mining, forced flotation recover over 90% of target metal, turning raw into profit. But it is not just about efficiency. These methods are sustainability game changers, recovering protein from dairy waste or clarifying water without chemical alliance with global clean growth. Where do we go from here? The future is smart and sustainable. Imagine centrifuge with AI that adjusts speed in a real time, or hybrid system combining microfluids and flotation for nanoparticle separation. We are moving toward zero waste processes where every particle is either a product or a research. So, not trash. In conclusion, whether you're designing a lab procedure or scaling up for industry, remember the right separation methods save time, money, and the planet. As we innovate, let's keep pushing for precision and sustainability. Thank you. Now,